Welcome to the deep dive.
Great to be here.
Today we are plunging into some really interesting source material from Ruby Kaigi.
Yeah, this is a talk by Koichi Sasada looking at concurrency and performance in Ruby. Loic Menet collaborated too, should mention that.
Right. And we're specifically diving into, well, a notoriously tricky piece of the puzzle, garbage collection.
Uh-huh. And not just GC, but how it interacts, or maybe how it needs to interact with Ruby's Ractors for, actual parallel performance.
Exactly. This source stack you've pulled together, it outlines a really fundamental challenge here.
It really does. Managing memory when things run in parallel,
Yeah.
it's tough. But it also proposes a pretty clever solution. Pragmatic, I'd say.
And one that's apparently showing some serious performance wins already, which is key.
That's the exciting part, yeah. Real numbers.
So the mission for this deep dive, let's lay it out. We need to understand why GC becomes such a headache with Ractors.
Like, what's the core problem when you go parallel?
Yeah. Then what's Ruby doing now? What are the limitations there?
Right. The current approach.
And then we really need to unpack this proposed conservative local GC strategy. How does it try to, cut through the complexity?
Even if it's not, like, the theoretically perfect answer, it's about trade-offs.
Exactly, trade-offs. We'll be looking at isolated object spaces, shareable objects.
Get ready for some aha moments, hopefully, as we explore that balance between, let's say, perfect accuracy and getting real speed.
Okay, let's get started. Setting the stage, Ractors, they landed in Ruby 3.0. Big deal. Remind us, what exactly are Ractors? What problem were they built to solve?
Right, so Ractors were basically Ruby's big push to enable true parallel computing, using all those cores modern CPUs have.
Because before Ractors, Ruby had threads, but there was the GVL.
Exactly, the global VM lock. The GVL meant that generally only one thread could run Ruby code at any single moment, even if you had 16 cores sitting idle. Kind of a bottleneck.
So Ractors were meant to break that GVL bottleneck, get actual parallel speed?
That was the primary goal, yes.
Yeah.
Use the hardware properly. But there was another angle, too.
Which was?
Robustness. Avoiding those classic nasty concurrency bugs.
Race conditions and things like that.
Precisely. And the key feature for that robustness is this idea of isolated object spaces.
Isolated object spaces, like walls between the Ractors.
Kind of, yeah. The basic rule is you, from inside one Ractor, cannot just reach in and fiddle with objects living inside another Ractor.
Okay, so no shared mutable state, that classic problem.
That's the target. By preventing different parallel bits of code from modifying the same data simultaneously, you eliminate a whole class of really hard-to-debug concurrency issues. It's about safety.
Got it. So mostly isolated worlds. How does the GVL fit into this picture then with Ractors? Did it just disappear?
No, not quite. And this is crucial. Each Ractor gets its own GVL.
Its own GVL, okay.
Yeah, so if you have multiple threads running inside a single Ractor, they still contend for that Ractor's GVL. They won't run truly in parallel with each other.
Okay, so threads within a Ractor are still limited.
Right, but because different Ractors have different independent GVLs.
Threads in different Ractors can run truly in parallel on different cores.
Exactly, that's the mechanism. The isolation enables independent GVLs, which enables true parallelism across Ractors.
Okay, that makes sense. Now, if each Ractor is mostly this isolated world of objects, what does that suggest for cleaning up memory? For garbage collection?
Well, it suggests a really natural idea, doesn't it?
Yeah, it kind of jumps out at you. If Ractor A is managing its own stuff and Ractor B is managing its own stuff...
Why not just let Ractor A run its own garbage collection cycle independently?
Right. Let Ractor A scan its own objects, figure out what's love, live for it, collect the rest.
All without stopping Ractor B or C or any others. They could just keep running.
You can almost picture it. Ractor A pauses briefly for its own cleanup while B and C keep churning away. And maybe B does its cleanup later, parallel GC.
Each Ractor starting from its own roots, marking within its own space, collecting locally. It's the concept of Ractor local GC.
Seems like the perfect fit for the whole Ractor isolation model.
It sounds perfect.
There's always a but. Here's where it gets, as you said, really interesting. That elegant, natural idea, it hits a pretty big wall.
A fundamental snag, yeah. And the snag has a name. Shareable objects.
Shareable objects. So, despite the isolation, some things can be shared.
Yes. While most objects live strictly within one Ractor, the system allows, and actually needs, some objects to be accessible by multiple Ractors. They're designed to be shareable.
Okay, the exceptions that break the simple model, what kinds of things are we talking about?
Think about fundamental stuff, like class definitions, module definitions. Method definitions, compiled bytecode.
Things that define the program itself, basically.
Right. Also, certain kinds of closures, ones that don't capture any non-shareable state.
Yep.
And even the Ractor objects themselves, so one Ractor can, manage another.
Okay, so infrastructure, definitions, immutable-ish data, stuff that makes sense to share without copying everywhere.
Exactly. It avoids unnecessary duplication and overhead for these common, often long-lived things.
So multiple Ractors can hold a reference, a pointer, to the exact same shareable object. How does that break our nice, simple Ractor local GC dream?
Okay, let's use the example from the source that makes it clear. Imagine Ractor 1 owns, or maybe just holds a reference to, a shareable object. Let's call it SH1.
Okay, Ractor 1 knows SH1.
Now Ractor 2 also gets a reference to that very same SH1. Totally allowed, it's shareable.
Ractor 1 points to SH1, Ractor 2 points to SH1. Got it.
Right. Now let's say Ractor 1 finishes doing whatever it needed SH1 for. Maybe the variable holding its reference goes out of scope within Ractor 1.
So from Ractor 1's local perspective, it's not using SH1 anymore.
Correct. Now Ractor 1's local garbage collector kicks in. Remember, it's designed to look only within Ractor 1's isolated space.
Okay, it stands from Ractor 1's roots.
And it sees, nothing here in Ractor 1 seems to be pointing to SH1 anymore.
So the local GC thinks SH1 is garbage.
It concludes SH1 is garbage from its limited perspective and might decide to free the memory associated with SH1.
Oh, but wait, Ractor 2 is still using SH1. It still has a valid pointer.
Exactly the problem. The local GC in Ractor 1, acting purely on local information, has no idea that Ractor 2 still needs SH1.
So if it frees SH1, Ractor 2 suddenly has a dangling pointer, pointing to garbage memory.
Which is a crash waiting to happen, a major memory safety violation. Freeing a live object is one of the cardinal sins of GC.
So the core issue is a purely local GC, blind to the outside world, can't safely collect a shareable object because another Ractor might still need it.
You've nailed it. The existence of these cross-Ractor references to shareable objects breaks the simple collect everything local approach.
Which naturally leads you to think, okay, what's the ideal fix? The source calls it solution 1.
Right. The ideal fix would be to somehow track these cross-Ractor references.
So if Ractor 1's GC was about to collect SH1, it could check some central registry and see, oh, wait, Ractor 2 still has a reference, don't collect it.
Logically, yes. If you had perfect up-to-the-millisecond knowledge of every reference to every shareable object across all Ractors, local GCs could make safe decisions.
Okay, that sounds great in theory. But the source makes it clear why this is, well, incredibly difficult. Almost a nightmare, practically speaking. Why?
It really comes down to the dynamic and parallel nature of it all. References change constantly. Ractor 2 might drop its reference to SH1 1 nanosecond, then Ractor 3 might pick one up the next.
Well, Ractor 1 is maybe trying to run its GC.
Exactly. Keeping track of who references what accurately across all these parallel, independently running Ractors. It's synchronization hell.
And if your tracking information is even slightly out of date,
boom. You might think an object is free when it isn't, or vice versa. Incorrect tracking could lead to freeing live objects, bad, or leaking memory. Also bad, just slower.
Plus the tracking mechanism itself, it must add overhead, right?
Huge overhead, potentially. You'd need things like atomic counters, maybe global lookup tables, ways for Ractors to constantly signal reference changes. All of that costs CPU time and memory itself. The source even had that tricky example with chain references, like SH1 points to SH3. Tracking that gets complicated fast.
Yeah, it sounds like one of those perfect is the enemy of the good situations. The theoretically perfect solution is just too hard or too slow in reality.
That's been the major blocker for Ractor local GC for a while now, the complexity of accurate cross-Ractor tracking.
Okay, so if perfect tracking is off the table for now, what is the current situation? Ruby 3.0 through 3.4, the master branch, how do they handle Ractor GC today?
Well, despite Ractors having these conceptually isolated spaces, the GC reality today is it's global. Ruby relies on a global object space and primarily uses a global GC mechanism.
Global GC.
Yeah.
Okay, how does that work when you've got potentially many Ractors running in parallel?
When GC needs to happen, say, memory runs low, the Ruby runtime basically hits a giant pause button. It stops all Ractors.
All of them, like stop the world.
Yep. A full stop the world pause. Everything halts. Then the GC runs. It traverses the entire heap, looking at objects from all Ractors, starting from the roots of all Ractors combined.
Wow. Okay, that sounds counterproductive to the whole parallel Ractor idea.
It absolutely is. That's the huge drawback. Now, the upside is it's perfectly accurate because it sees everything. It knows all the references, including the cross-Ractor ones. It won't mistakenly free a live object.
And maybe space efficient, since free memory is just one big pool.
Yeah, that's another pro. Free slots can be reused by any Ractor. But the performance cost,
It must kill parallelism.
totally. It serializes the garbage collection process completely. You could have 16 Ractors ready to do useful work, but if one triggers GC, all 16 stop and wait.
And the more Raptors you add, allocating objects.
The more often the global GC might get triggered. So paradoxically, adding more Ractors doing work could actually slow down your application because you hit this serial bottleneck more frequently.
Right. If you picture the timelines, local GC might have short, independent pauses, while global GC is this big synchronized stop sign for everyone.
That's a great way to visualize it.
Yeah.
Global GC explicitly blocks the parallelism Ractors were meant to enable.
Okay, so the goal is still local GC to avoid that bottleneck, but perfect tracking is too hard. This brings us to the proposed solution in the talk. How do they try to thread this needle?
This is where the pragmatic, kind of clever compromise comes in. It's described as a conservative Ractor local GC,
Conservative.
meaning it plays it safe. The core idea is, when a Ractor runs its local GC, it simply doesn't try to do that complex cross-Ractor reference tracking for shareable objects.
Okay, so it ignores the problem. What happens when its local scan doesn't see a reference to a shareable object anymore? Does it just free it and hope for the best?
No, that would be unsafe. That's where conservative comes in. Instead of trying to track, it makes a simple, safe assumption. During its local GC, it treats all known shareable objects as if they are always reachable, like they're permanent routes.
Ah, so the local GC just says, anything marked shareable, I'm not touching. I assume someone, somewhere, might still need it.
Precisely. It prevents the local GC from ever collecting a shareable object, thus avoiding the dangling pointer catastrophe.
Okay, that guarantees safety. But doesn't that mean memory leaks? If a shareable object becomes truly unreachable by everyone, but local GCs always keep it alive.
You're exactly right. That's the trade-off. Shareable objects that are genuinely garbage, no Ractor anywhere needs them anymore, won't be collected by these local GC cycles. They will stick around longer, using up memory.
So you're trading potentially wasted memory for parallelism and safety?
That's the core exchange. You accept some potential memory bloat from lingering shareable objects in return for letting local GCs run independently and in parallel most of the time, which unlocks performance.
But you can't just let that memory leak forever. How do you eventually clean up those truly dead shareable objects?
That's the other part of the strategy. They still use the existing global GC mechanism, the stop the world one.
They fall back to it.
Exactly. They fall back to running the full, accurate, stop the world global GC periodically. Because that GC does see everything, it can correctly identify and collect shareable objects that are truly unreachable by any Ractor.
Okay, so local GC handles the bulk of the garbage, the non-shareable, Ractor local stuff quickly and in parallel. Then, much less often, you have a global GC pause to clean up the leftover shareable garbage.
That's the plan. The key is that because local GC does most of the heavy lifting, you can run the slow, blocking global GC much less frequently than you have to today. You remove the frequent bottleneck.
That makes a lot of sense. It's pragmatic, it gets you most of the benefits of local GC without solving the impossible tracking problem right now.
It really embodies that philosophy mentioned in the source. Done is better than perfect. Find a workable solution that delivers significant gains now, rather than waiting indefinitely for perfection.
So did they actually test this, put the conservative approach through its paces? What did the benchmark show?
Oh yeah. The talk included Microbenchmark results. They compared the current Ruby master branch, using the global GC, against a version with this proposed conservative local GC. Ran it on a multi-core machine, of course.
What kind of scenarios?
Well, one classic scenario. Lots of Ractors, allocating, and then quickly discarding short-lived strings, all local to each Ractor. Very common pattern.
Okay, how do they compare?
The results were pretty stark. The local GC version scaled really well. More Ractors meant significantly more throughput. The master version, though, it hit that global GC wall. The source said it showed almost no parallel benefits.
Wow. So the global GC was just bottlenecking everything, any numbers.
Yeah, they showed speed-up ratios.
Hmm.
Like with 16 Ractors, the local GC version was apparently getting close to a 5x speed-up compared to the single Ractor baseline. The master version speed-up just flattened out completely.
A 5x improvement just by changing the GC strategy in that case. That really highlights the cost of that stop the world pause.
It's a clear demonstration. Then there was another benchmark, Ractors creating lots of long-lived Ractor local arrays.
Okay, how did that play out?
This one was maybe even more telling. The master version actually got slower as they added more Ractors.
Slower, with more cores.
Yeah, because more Ractors allocating long-lived stuff triggered the blocking global GC more often, dragging everything down. The local GC version, however, handled it, quote, very efficiently. It kept scaling up, achieving over 4x speedup with 16 Ractors in that test too. Getting worse performance with more resources is like the definition of a scalability bottleneck. That's damning for the current global approach. It really isolates the issue. They also ran a simpler regex matching benchmark, and the local GC version showed good improvements there too, though maybe not quite as dramatic.
So, boiling it down, what do these benchmarks tell us? What's the takeaway for someone thinking about using Ractors?
I think the strong signal is that this conservative local GC approach really works. It successfully leverages parallelism for Ractor local work, especially involving object allocation. By drastically cutting down on those global GC pauses, it removes a major performance bottleneck and lets Ractors actually run faster in parallel, delivering on their promise.
This sounds like it could be a really big deal for making Ractors practical and performant in real-world Ruby apps. What's the roadmap for this? When might we see it?
The stated goal in the talk was to get this implementation finished and merged for Ruby 3.5. So that's the target they're aiming for.
Okay, Ruby 3.5. Are there other things happening in this space, related work on GC or Ractors?
Yeah, they've briefly mentioned ongoing work to improve the global GC itself, like adding parallel marking to it. That helps make even those infrequent global pauses faster.
Makes sense. Optimize all the pieces.
And interestingly, they didn't completely shut the door on the ideal solution one, the perfect tracking. It was noted that maybe someone, perhaps Loic Menon, is still exploring if a feasible way to do that might exist down the line. But the conservative approach is the focus for now.
Right. Get the big win now. Keep researching the harder stuff. I think I also saw a quick mention of something about Ractor ports and the lock API. Is that related?
Ah, yeah, that was mentioned quickly. It's a separate, though related, proposal aimed at improving how Ractors communicate with each other, potentially avoiding traditional locks. It just highlights that this whole area, Ractor performance, memory, communication, is really active right now in Ruby development. Lots of moving parts.
Okay, so let's try and wrap up this deep dive. We've journeyed into the pretty complex world of Ractor local garbage collection in Ruby.
We definitely did, and we saw that while Ractors give us these nice isolated spaces for parallelism, the fact that some objects have to be shareable creates this fundamental headache for local GC.
Right. Doing it the perfect way, tracking all those cross-Ractor references accurately seems just too hard or too slow for now. A major challenge.
And the current method, just stopping everything for a global GC while safe, really undermines the whole point of Ractors by killing parallelism. It becomes a bottleneck, especially as you scale up.
Which makes this proposed conservative approach so interesting. It's a clever compromise, isn't it?
It really is. Treat shareable objects, as always, live during local GC, except that some might hang around a bit longer than needed.
But gain the huge win of letting local GCs run in parallel most of the time. Then use an infrequent global GC just to sweep up the leftovers.
It's a great example of pragmatic engineering. Focus on getting something done that delivers real benefits, even if it's not theoretically perfect.
Yeah, this dive really shows how moving forward in complex systems often means finding those smart trade-offs, focusing on measurable progress rather than waiting for an ideal that might never arrive.
Absolutely.
So thinking about all this, it leaves us with a question for you, the listener. As Ruby keeps improving its concurrency story with Ractors, with better GC like this coming down the pipe, making better use of all that hardware out there, what new possibilities does this open up? What kinds of parallel apps or performance boosts in existing ones might you be able to build or unlock in the future?
Something to think about. Thanks for joining us on this deep dive.